All right, guys. So today we're going to start solving trig equations algebraically. And a lot of what we've done with the identities will help us with this, especially the factoring aspect when we, did quite a bit of factoring trigonometric expressions. All right. And then we'll continue to build on this with a couple of different, um, identities, you can call them, but they're formulaic. We'll talk about the sum and difference angle formulas and the double angle formulas. And we'll kind of continue to build on solving equations as we add those. But we're going to start very simple today. All right, so this says solve each equation on the interval from 0 to 2 pi. Do note that 0 is included and 2 pi is not. Okay, that's because they're coterminal angles, right? We can think of them mathematically as the same angle, the same position on the unit circle. All right, so we only need to count that position one time. So we count that as 0. Okay, so typically when we solve equations, we try to isolate the variable, right? Well, in this case, when we're solving trigonometric equations, all right, we are going to try to isolate the entire trig function. All right, so in this case, we're trying to get sine of x by itself. All right, so if we think of sine of x as my variable, what do I want to do first to get it by itself? What's that? Yeah, add 1 to both sides, right? So we add 1 to both sides. This will cancel. We get 2 sine of x is now equal to 1. All right, well, I'm still trying to solve for sine of x here. So what do I need to do next? Divide by 2. All right, so now I have sine of x is equal to 1/2. All right, now before, when we did stuff like this, we would have taken an inverse sine, right? And then we would have just had x equals, whatever we got when we did our inverse sine. Of course, inverse sine only deals with the right half of the unit circle, right? Here, it says to look at the entire unit circle, right? So all we do here is we say, okay, where on my unit circle is sine of x 1/2? All right, well, remember, sine is my y coordinate. So I go pi over 6 is one of them. And where else? And 5 pi over 6, absolutely, right? So here's a y coordinate of 1/2 at 5 pi over 6. Here's a y coordinate of 1/2 at pi over 6, all right? So we can simply say x is equal to pi over 6 and 5 pi over 6. And that's it. That's all there is to it. All right, so we're going to be kind of using the unit circle extensively again with this unit. So what do you think is going to be coming up soon? A unit circle quiz. All right. Guys, remember I did tell you that there would be 3 of them throughout the course of all of our trig units. All right. You've taken 2 so far. All right. So you'll have 1 more. All right. Do remember that, of course, each of them count as a quiz grade, but do also remember that I told you I'd be averaging those 3 quizzes, right? And that will count as a test grade as well. So the unit circle is incredibly important. Not only in trig, but as you go forward in calculus as well, right? Your calculus teacher will expect you to know the unit circle inside and out when you get there, right? I mean, he may review it briefly, but he's not going to take the time to teach it to you again like I've taught it to you and like we've extensively used it, right? So it is, especially if you plan on going on to calculus, which the vast majority of people in honors pre-calculus do, all right, it's very, very important to know that. Okay. This one will work very similarly to the last. Why don't you guys take a brief moment to try to work this out? All right, so this should go relatively quickly. All right, so first we add square root of 3 to both sides, and then we divide by 2. So cosine of x is equal to the square root of 3 over 2. All right, so then we go ahead, we go to our unit circle. We say, where is cosine of x? The square root of 3 over 2. All right, of course, cosine is our x coordinate on our unit circle. So that occurs here at pi over 6 and here at 11 pi over 6. All right, so we say x is equal to pi over 6 and 11 pi over 6. And that's it. All right, very straightforward. All right, so now we have signs on both sides, but that's really not a big deal, all right? Just like whenever you were in Algebra 1 and you had variables on both sides of the equation, all right, that's fine. We still just always want to get our variables on one side and our constants on another, right? But now with trig functions, right, we're trying to get our trig expressions on one side and our constants on the other, right? So there's a couple of ways that you could do this, but I'll just go ahead and add sine to both sides. This way we'll actually take an extra step, but a lot of people prefer positive variables, or in this case, a positive trig expression, right? So now we will have 2 sine of x, right? Just like x plus x is 2x, sine x plus sine x is 2 sine x, all right, plus the square root of 2, and now that just equals 0. So now this looks exactly like one of the problems that we just did. So I'll go ahead and subtract square root of 2 from both sides and then divide both sides by 2. So now we say sine of x is equal to negative square root of 2 over 2. All right, so now we simply just go to our unit circle. Sine is our y. All right, where is my y coordinate? Negative square root of 2 over 2. That occurs here at 5 pi over 4. And that also occurs here at 7 pi over 4. So we simply say x is equal to 5 pi over 4 and 7 pi over 4. Any questions or concerns thus far? It's pretty straightforward to this point. All right. Okay, so now we have a squared term. That's okay. All right. So we still are trying to isolate our trig expression here. So first I'm going to add 1 and then divide by 3. So we will have tangent squared x is equal to 1/3. All right. So we don't care about tan squared x, we just care about tangent of x. So how do we undo a square? Square root. All right, so now we have tangent of x is equal to, all right, and remember when you take the square root of a fraction, you take the square root of the top and the square root of the bottom. The square root of the top, of course, is just 1. The square root of bottom is the square root of 3. All right, of course, we can rationalize this, and this will become the square root of 3 over 3. Now, we do have to be careful, all right? When we take a square root, technically, what is it supposed to be? What's the square root of 9? And? Yeah, right? So this is actually plus or minus square root of 3 over 3, right? And this is probably the most common mistake, on a test or quiz with something like this. You just forget to take the plus or minus, and therefore, you'll only give the values of x that would give that positive square root of 3 over 3, and you would miss the 2 that would give you the negative, right? So you would miss a couple of points there. All right, now, yeah, it's always going to be plus or minus. Exactly. Yeah. All right, so now I won't stick to that it's always 4 because as you see later, once the period changes, that'll change too. But in general, yeah. Okay, so Now, our unit circle here doesn't have our tangents on it. All right. I will go ahead and write tangents on it, though. All right. When we first started talking about the unit circle, so on your unit circle that you have filled out, hopefully you did put all of those tangents around here. Remember, to get the tangent, of course, you just take the y-coordinate divided by the x-coordinate. All right. So here you would get 0. All right. Here, once you divide and rationalize and stuff, you get the square root of 3 over 3. All right, and then you get 1. Here you get the square root of 3. Here you get undefined. All right, now of course you can simply reflect these all over and kind of, whenever you have one negative and one positive for your x and y, then it's going to be a negative value. Whenever you have both positive or both negative, you're going to have positive values. All right, so this would be negative square root of 3, negative 1, negative square root of 3 over 3, 0, positive square root of 3 over 3, positive 1, positive square root of 3, undefined again, all right, negative square root of 3, negative 1, negative square root of 3 over 3. All right, so we were looking for plus or minus square root of 3 over 3. So that occurs, we have a positive 1 here at pi over 6. We have a negative 1 here at 5 pi over 6. We have a positive 1 here at 7 pi over 6. And a negative 1 here at 11 pi over 6. All right, so here x is going to equal pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. All right, so same concept, just we had to remember that plus or minus. All right. All right, go ahead and try this one. It will work much the same. No, it's not. Honestly, compared to verifying trig identities, I think this is kind of a piece of cake.
That's hard because, like, there's no certain ways to
do it. Exactly. Now we're back to, algorithmic mathematics, where you do this, then you do this, then you do this, and you're always going to be in the right place. All right, so like I said, this works much the same, right? So first I'm going to go ahead and add 3 to both sides, then divide by 4. So we end up with sine squared x is equal to 3/4. Of course, to undo my square, I do the square root. So now I just get sine of x. Again, we do have to be careful about that plus or minus. All right, the square root of 3 can't be simplified. It's just the square root of 3. And the square root of 4 is 2. All right, so now we're looking for whatever sine of x is positive or negative square root of 3 over 2. So we look at our unit circle. All right, sine, of course, is y. So here we have square root of 3 over 2 at pi over 3, square root of 3 over 2 at 2 pi over 3, negative square root of 3 over 2 at 4 pi over 3. right? And negative square root of 3 over 2 at 5 pi over 3. So those will be all of my solutions. So x is equal to pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. And we're done. Okay, so now we get to a slightly different type of problem, which is perfectly fine. All right. So whenever you have one sine or any trig expression that's squared, and then that same trig expression that is not squared, right? We still do want to get them on the same side, right? So I'm going to subtract 2 sine x from both sides, and I will get sine squared x minus 2 sine x is equal to 0. All right, now, guys, these work just like x squared and x would work, right? Because they have different exponents, they are not like terms. You cannot combine them, right? Every year I have somebody who tries to tell me that this is magically like negative sine x or, negative sine squared x, right? No, they are not like terms. They can't be combined, right? So just like if I told you that we had x squared minus 2x equals 0, how would you solve that? What would be the easiest way to solve it? There's multiple, but yeah, right? You would factor an x out, and you'd be left with x minus 2 equals 0. And then you'd set each one of these factors equal to 0, right? And there would be your two solutions. This works the exact same way, all right? That's the beautiful thing about math, right? I say this all the time. Math always works the exact same way, literally always, all right? It just gets a little bit more complicated, right? So instead of dealing with x's, now I'm dealing with sine x's. Do you have a question? No. Okay. Right. So yeah, all I have to do is say, all right, let's factor out a sine x, and I'm left with sine x minus 2, and that's all equal to 0. Right. Again, whenever I have two factors set equal to 0, I can set each factor individually equal to 0. So we have sine x is equal to 0. Whoops. And sine of x minus 2 is equal to 0. So of course we can solve this and say sine of x is equal to 2. Okay, so now we say first on our unit circle, where is sine of x equal to 0, right? Well, again, sine is my y coordinate. Sine is 0 here at 0, right? And sine is 0 here at pi. All right, so we go back here, we say, okay, well, for this piece, x is equal to 0 and pi. All right, so now we say, okay, well, where is sine of x equal to 2? All right, well, we go and we look at our unit circle. Oh, well, there's no y coordinate that ever says 2. All right, well, awesome. Well, now, also, guys, what is the range of sine? Like our graph, just our parent function. Remember, it's the little wave. If my amplitude is just 1 and my baseline is 0, I go down to -1 and I go up to +1, right? So if that's the case, do I ever get to 2? No, right? So it actually is never going to happen. So here you just say that, the null set, right? There's nothing. Or you can just say no solution, right? No solutions. No, not at all. Like these are your actual solutions that will work for this equation. Okay. But just for that piece, you do need to signify that from that specific factor, there are no solutions. Does that make sense? Okay. Yeah, I like for all of the work, like the actual answers, these are your answers. But I give, like I would give you a point for this step. I would give you a point for factoring. I would give you a point for setting each factor equal to 0, right? I would give you 2 points for getting these two solutions. and I would give you a point for telling me like that there are no solutions here. Do you know what I mean? So the actual answers to this equation are only 0 and pi. Okay. But as far as all of your work that I give points for, I would want to see all of it. Okay. So now we're going to shift slightly, and we're going to talk about finding all solutions of each equation. All right. Now, all solutions aren't just the solutions on the unit circle. Remember, you can go around the unit circle in both the positive and the negative direction as many times as you want. All right. So how many solutions are there going to be? What's a word for a really, 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 yeah, there's going to be infinite solutions, right? Because you can go around the circle as many times as you want. All right. And we've kind of seen this notation a little bit when we were talking about the x-intercepts and vertical asymptotes of trig functions when we were talking about the graphs of them, right? And we talked about that like plus n pi type thing. All right, that's going to come into play here as well. All right, so what does this look like? It looks like a function you can factor. It looks like a quadratic function, right? Remember when we talked about these a few days ago, we said, okay, well, if we just let u equal cosine of x, whoops, all right, then that means u squared would have to be cosine squared x. So if we replaced that in this equation, we would get 2u squared minus u minus 1 equals 0. Okay, well now that looks exactly like quadratics that we've been used to solving our entire lives, right? Now, guys, if you just see the quadratic with the cosine in it, right, you don't have to switch it to u's, right? I know that in this class, um, there's probably, oh, I don't know, at least 3 or 4 of you that just look at it and see it, right? And you're like, yeah, I don't need to, put u's in there. You don't have to do that, all right? But it can help. Those of you that struggle with factoring a little bit or don't like factoring and definitely don't like, having to factor with cosines and cosine squareds and stuff, this can just be a tool that helps you, okay? But I don't want you to think that it's required to put in the u's, all right? It certainly is not. Okay, so here, all right, my leading coefficient is something other than 1. So I'm going to go ahead and use my trash can method. A times C is -2. B is -1. So numbers that multiply together to give me -2 but add together to give me -1 are -2 and +1. All right, so I keep my leading coefficient here in both of my factors. I fill in my blanks with the numbers I just found, -2 and +1. All right, now obviously we can't keep all of this stuff because 2u times 2u is not 2u squared. All right, but that's why this is called the trash can method. We have to pull out our extra stuff. All right, so we look at each factor and say, is there something that I can pull out of here? Yeah, I can pull out a 2 there, and I'm left with u minus 1. Here, nothing can be pulled out, so I have to keep it 2u plus 1. All right. Of course, it's called the trash can method because whatever we pull out in that step gets thrown away. All right, so this is my factorization. Of course, I'm not dealing with u's. All right, I'm dealing with cosines. All right, so this is really cosine x minus 1 and 2 cosine x plus 1. All right, so I set each of these equal to 0 and solve. When I set this equal to 0 and solve, I will get cosine of x is equal to 1. When I set this equal to 0 and solve, I will subtract 1, divide by 2. So cosine of x is equal to -1/2. All right, so here we look at our unit circle. First, where is cosine of x equal to 1? All right, well, cosine is the x coordinate. That occurs right here. And that's it. That's the only place, right? So there we have x equals 0. All right, now we need to say, okay, where is cosine -1/2? So I go back to my unit circle again. All right, cosine is my x. All right, oh, well, here's -1/2 here at 2 pi over 3. And here's -1/2 here at 4 pi over 3. So I say x is equal to 2 pi over 3 and 4 pi over 3. And that's it. These are my three solutions that will all work for this equation. Questions or concerns? Right? So this is just a combination of when you used to solve quadratics in Algebra 2 a lot, right? And kind of mixing it in with our unit circle stuff with trig functions. Try this one. Okay, so the nice thing about this equation here is that it's the exact same as this equation here, right? But just with signs instead, right? So the factorization is actually going to work the same, right? So of course, if you went through the whole process, that's perfectly fine. We can go ahead and do that, right? So 2 times -1 gives me that -2, and here's -1. So of course, again, we have -2 and 1, right? So we would have 2 sine x minus 2 and 2 sine x plus 1. Of course, we'd have to pull a 2 out here and throw it away, and we'd be left with sine x minus 1. Nothing comes out of here, so that stays 2 sine x plus 1. Set each of these equal to 0 and solve. Here we will get sine of x is equal to 1. And here we will get sine of x is equal to negative 1/2. So if we look at our unit circle, all right, sine of x is equal to 1 here at pi over 2, and sine of x is equal to negative 1/2 here at 7 pi over 6, and here at 11 pi over 6. So here we said x is equal to pi over 2, and here we say x is equal to 7 pi over 6 and 11 pi over 6. And we're done. Any questions or concerns over that problem? Sweet. Okay. All right, so here we have two different trig functions. We don't like that, right? We want them to be the same, right? Now, we do have an identity that says 1 plus tan squared x is equal to secant squared x. All right, so I'm going to want to replace, of course, as I always say in mathematics, whenever two things are equal to each other, they are interchangeable. So wherever you see one, you're allowed to put the other. Well, so wherever I see a secant squared x, I'm allowed to replace it with 1 plus tan squared x. I see a secant squared x here, so I'm going to replace it. So I have my 3. Instead of secant squared x, I'm going to replace that with 1 plus tan squared x. And then I still have my minus 2 tan squared x minus 4 is equal to 0. All right, now I do have to distribute this 3, all right, so do be mindful of that. All right, so now I'm going to have 3 plus 3 tan squared x minus 2 tan squared x minus 4 is equal to 0. All right, so now I have like terms, right? I have this 3 and this negative 4, and I have this 3 tan squared x minus 2 tan squared x. All right, so 3 of some, I like to think of these as tangible things as to not confuse myself, right? If you think of tan squared x's as apples, right? So if I have 3 apples and I take 2 apples away, how many apples do I have? Yeah, right? So this just becomes 1 tan squared x. And then, of course, 3 minus 4 is negative 1. Now, there's two ways that you can do the problem from here, right? You can either use square roots or you can factor, all right? Square roots is probably a little bit easier, but you're much more prone to missing one of the solutions, all right? Whereas factoring requires a little bit more writing, but you're guaranteed to not miss a solution, okay? So I like to show it as factoring, but I'll show you both ways, just, so if you have one strong preference over the other. All right, this is a difference of perfect squares, right? So I can actually factor this to tan x plus 1 and tan x minus 1. So of course, when I set each factor equal to 0 and solve, here I would get tangent of x is equal to negative 1, and here I would get tangent of x is equal to positive 1. All right, so of course from here we can go back to our unit circle. All right, and we're talking about tangent, which is all of these red things around here. All right, so, well, tangent is 1 at pi over 4 and 5 pi over 4, and tangent is negative 1 at 3 pi over 4 and 7 pi over 4. All right, so tangent is 1, we said, at pi over 4 and 5 pi over 4, and it's negative 1 at 3 pi over 4 and 7 pi over 4. All right, now, I said that I'd show you another way to do it, all right, so I will. All right, so taking it from this, we could just say, okay, well, let's just add 1 to both sides. right? Then I have to take the square root. So now I have tangent of x is equal to, now a lot of people here just say 1, right? But we have to remember to say plus or minus, all right? So if you know that you're going to remember the plus or minus, then that's fine. It takes us right back to here. Okay, well, it's 1 or positive 1 at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4, all right? But so many students forget that minus that if you do it this way, you're much more susceptible to missing 2 of the answers. Does that make sense? Okay. But either way, of course, will work. All right. Go ahead and try this one. It will work much the same. Of course, whenever we have squared trig functions, we're always going to be using a Pythagorean identity to replace it, right? And just like when we were factoring them, before we were solving them, when we were just factoring them, we're always going to be changing the squared term. We'll never change the linear term, the first degree power term.
So we're going to change the sign. That's right.
Yes. I don't believe it. I don't know why you'd lie to me like that. Just to let you know, when I'm presenting, I can't see what's going on in the Google Meet room. I never would have known. I'll trust you. If this were a foundations of algebra class, then I would assume that you were sitting there doing nothing. But in an honors pre-calculus class, I assume most people are at least quasi paying attention.
That was so funny when people would walk in 4 times before the actually showed up.
That's why we finished. I think all more people have to go that way. That's why we finished.
I did with that.
I know. Friends is the only person I talk to. Like, yeah, people are really like involved.
Yeah, we have like 3 more people. Oh,
Normally,
you're
they're
not.
like, alright.
Yeah, we didn't start ours till 8.
Only promotion is their first one. That's the only reason they would have done that in
Yeah, in IB, they don't like whatever time the test starts, the time the test starts. You ready? You can't get ready.
Yeah, they were usually sitting in your seat by 8. But we didn't even start talking until 8:30 because we were waiting on people. I just didn't know what was I saying, so I just felt like he didn't have to go.
Mhm.
Oh, you late bird, you got some good on it.
All right, guys. So, of course, we want to change this trig expression that is squared. So we're going to use our Pythagorean identity of sine squared theta plus cosine squared theta is equal to 1. So if I'm trying to replace sine squared, I need to solve for sine squared. All right. So I subtract cosine squared from both sides. So sine squared theta is equal to 1 minus cosine squared theta. All right, so of course, whenever two things are equal, they are interchangeable. So wherever I see sine squared x, I'm allowed to replace it with 1 minus cosine squared x. So that's what I will do. And of course, we have to distribute here. So 2 minus 2 cosine squared x plus 3 cosine x minus 3 is 0. I need to combine like terms. Of course, I can't combine my trig terms because one is squared and one is not. But I can do 2 minus 3. All right, so I get negative 2 cosine squared x plus 3 cosine x, and 2 minus 3 is negative 1. All right, now, we're going to have to factor this. All right, I hate factoring with a negative leading coefficient. You can either take a negative out or just multiply both sides of the equations by negative 1. Right? And then, so if you change, basically you just change the sign of everything once it's set equal to 0, right? So this is the same as 2 cosine squared x minus 3 cosine x plus 1 still equal to 0. Because 0 times negative 1, still 0, doesn't affect it. Okay. So now we can go ahead and factor. All right, I have 2 times 1 is 2, and I have a negative 3. All right, so this will have to be negative 2 and negative 1, because negative 2 times negative 1 is positive 2, and negative 2 plus negative 1 is negative 3. So, of course, I keep my leading coefficient here. So I'm going to have 2 cosine of x minus 2 and 2 cosine of x minus 1. Everybody good so far? Say that again. You good? Okay. All right, so now we just take each factor, set it to equal to 0 and solve. So when I take this first factor equal to 0 and solve, I will add 2 and then divide by 2. So cosine of x, I'm sorry, I'm not done factoring yet. All right, so this is the trash can method, right? So I need to look for common factors in both of my factors. Here I can pull out a 2, and I'm left with cosine of x minus 1. And of course, trash can method, we throw that away. I can't pull anything out here, so it stays. And that's our factorization. So now I take each factor equal to 0 and solve. So when I set this equal to 0 and solve, I will get cosine of x is equal to 1. All right, and here I will get cosine of x is equal to 1/2. All right, cosine of x is equal to 1 at 0, right here. All right, and cosine of x is equal to 1/2, all right, at pi over 3 and 5 pi over 3. And there are all of our solutions. Good times? Had by someone somewhere? I mean, it could be worse. You could be my IB class. They're taking their IB test right now. So you are having better times than them, right? Okay. All right, so solve each equation on the interval 0 to 2 pi. All right, we have 2 cosine of 3t minus 1 is equal to 0. All right, what is the difference between this and any one we have seen so far? Yeah, there's a multiplier of my argument, right? So instead of just having an x or a theta or whatever, we have a 3, all right, in there. All right, so we do have to be very careful with that. All right, We don't want to mess with that 3 until the very, very end. Okay, I'll show you what I mean there in a moment. All right, so I'm still trying to get my trig expression isolated. All right, but I'm not messing with that 3. I just want to get cosine of 3t by itself. All right, so just like normal, I would still add 1 first and then divide by 2. And we get cosine of 3t is equal to 1/2. Okay, now, all right, what we do not do, all right, is divide by 3. So many students make the mistake here of, oh, if we divide by 3, then that's just cosine of t. No, no, it is not. Right, that's not how that works. All right, what we actually want to do is just pretend like this is regular cosine t. And we want to say, okay, where is cosine 1/2? Right, in fact, I think we just did this. Right, cosine is 1/2 at pi over 3 and 5 pi over 3. All right, so we have pi over 3 and 5 pi over 3. All right, however, instead of saying x, or in this case t equals, all right, we say 3t is equal to these things. Okay, well now there's no cosine there that's going to mess up me dividing by 3. All right, so I can go ahead and divide by 3. Dividing by 3 is the same thing as multiplying by 1/3 when you're dealing with fractions, so that will make it much easier. All right, so here I'm going to get t is equal to pi over 9, and here I'm going to get t is equal to 5 pi over 9. All right, now it's tempting to think that we are done right here. Okay, we are not quite done yet. I'm sorry that you drew your boxes prematurely. All right, so it says on the interval 0 to 2 pi. All right, now when we talked about graphing this thing, what letter would this represent? Remember, we would have our a times cosine of bx minus c plus d. It's b. What does b affect? The period, right? So we know that our period is equal to 2 pi over b, all right, which in our case is 2 pi over 3. Right? That means that my solutions repeat themselves every 2 pi over 3. All right? So now we want common denominators here. So this is going to be 6 pi over 9. All right? So if I add 6 pi over 9 to this, I'm going to get the same solution. My solution is going to repeat. So what do I get when I add 6 pi over 9 to this? 7 pi over 9. Is that still between 0 and 2 pi? Yes, the way to check is 7 over 9 between 0 and 2. Yes, and we're not even to 1 yet, right? Because 9 over 9 would be 1, right? So if I add 6 pi over 9 again, what do I get? 13 pi over 9. Is that still between 0 and 2? Yes, 13 over 9, definitely not 2 yet, right? What if I add 6 pi over 9 again? 19 pi over 9. Right, very good, Malcolm. All right, so yes, all right, if we do it again, we get 19 pi over 9. All right, well, 18 over 9 is 2. So 19 over 9 is bigger than 2. So we're outside of that range that we're trying. So this is it, right? We can't go anymore with this set. What if I add 6 pi over 9 down here? 11 pi over 9. Very good. And of course, if I add any more, I get too big. So those are all of my solutions. Don't switch the screen. How about I scroll down so that smart notebook not in your way?
Okay, you're good now.
We're good? Okay. Is everybody okay with that? All right, because really that's kind of like the trickiest thing that's going to happen.
So we're using three as our B.
What's that? You didn't see it?
So we're using the 3 as the B.
Yes.
Mine is still fast, and I've repeated it 3 times.
Excellent. Excellent. Technology's great when it works. That's a you problem. Okay. Try this one.
So then we just
She's
look
trying
at
to
it,
buy
look at it as sin x and then pi over 3 over 2, and after that.
Exactly.
It's not going to be plus or minus, right?
No, because we're not doing any square root stuff. For a small fee of $99.99. What's that? That there's a what interval? Yeah, that's the same, 0 to 2 pi. Yes. Yeah.
You don't divide another. Well, not.
Good question answer every question of the exam a little higher. We're kind of related.
But what are? I didn't say it. I just said it was right in there. But what? Yeah, I'm trying to know. Can you raise to like 2 2b is equal to 2 pi, 1b is 10. We can't be over 2 pi.
No, 2 pi cannot be included.
Okay.
We include 0, we don't include 2 pi. Just gonna wait this one out. Okay, so let's go ahead and look at it. All right, so of course, first I just add square root of 3 over 2 to both sides. So we get sine of 2x is equal to the square root of 3 over 2. All right, remember, we don't worry about this 2 yet, right? All we do is say, okay, where is sine? Square root of 3 over 2. So sine is square root of 3 over 2 here at pi over 3, and here at 2 pi over 3. All right, so we say, all right, well, 2x is equal to pi over 3, and 2x is equal to 2 pi over 3. So now I can divide by 2, which of course is the same as multiplying by 1/2. All right, and that's going to give me, okay, well here x is going to equal pi over 6, and here x is going to equal 2 pi over 6, which is pi over 3. All right, so of course now we want to figure out, all right, well, what is my period? Eventually you'll have to reduce it. For your final, for like when it's your final answer, eventually you're going to have to reduce it. You can reduce it whenever you want. Like if you want to, like when you're adding your stuff, do it and then reduce it later. That's fine. Right. Yep, that's fine. I mean, but eventually you're going to want to reduce it. All right, so period, of course, is 2 pi divided by b, which is 2. All right. So yes, this is just pi. All right. So of course, for this one, you can think of it as pi over 6, right? For this one, I'm sorry, 6 pi over 6. For this one, you can think of it as 3 pi over 3. You just want common denominators, right? So here, when I add pi, I'm going to get 7 pi over 6. If I try it again, I'm going to get 13 pi over 6. 13 over 6 is bigger than 2. So that's as far as we can go. All right, here I'm going to add 3 pi over 3, which is going to take me to 4 pi over 3. If I try to do it again, I get to 7 pi over 3. 7 over 3, larger than 2, so we have to stop there. Yes? It can't be larger than 2 pi, and that's because the directions from previous, right? Like this is just under the same set of directions. It gave us this interval, right? So all of our solutions have to be between these two numbers. Does that make sense? Okay, so this is going to work very similarly. All right, so we'll do another one. All right, well, where does see now here? Now do be mindful that x over 2 is the same thing as 1/2 x. Right? Yes, no, maybe so. All right, now, if we divide a pizza in 2, how much of that pizza do you get?
Half.
Half.
Oh.
So yes, dividing something by 2 is the same as cutting it in half. All right, so be mindful here that our b is going to be 1/2. All right, so here we don't really have anything to do. We just want to say, okay, where is tangent 0? All right, well, tangent is 0 here at 0, and tangent is 0 here at pi. All right, so we know that 1/2 x is equal to 0, and 1/2 x is equal to pi. All right, well now I need to essentially divide by 1/2, but that's just the same as multiplying by 2. All right, so here we get 0, right? So here we will get x is equal to 0. Here we get x is equal to 2 pi. Are we allowed to actually include 2 pi? No. All right, so we actually just say, nope, no sir, can't use that one. All right, now we do want to check on our period here. All right, and this is 2 pi divided by b, which is 4 pi. Okay, well, if I add 4 pi, I'm bigger than 2 pi.
But I got a question, where do you get pi from? Whenever you did 1/2 x equals pi.
Okay, so originally we just said, where does tangent equal 0?
Oh, okay.
Right? And tangent equals 0, which are all my red ones here,
I got you.
at 0 and at pi. Does that make sense? Okay. So this is going to be my only solution between 0 and 2 pi. Right, now it is important to note that this thing has infinite solutions, right? It has 0, 4 pi, 8 pi, 12 pi, 16 pi, right? Negative 4 pi, negative 8 pi, 2 pi, 6 pi, 10 pi, 14 pi, right? Negative 2 pi, negative, But the only one between 0 and 2 pi is 0. All right? So I don't want you to think that like all of these other things that we're talking about aren't actual solutions. They are. They're just not within the window that we were asked to look. Okay?
Will they expand on it though?
Yeah. Mm-hmm.
Wait, where did you get that two divided by b by 1/2? Oh, no.
That's what we
This is,
know. We need to decipher that all.
just time to call it quits. All right, guys, go ahead and try this one.
It's just gonna be negative 3 or negative 1.
Yeah, I think something funky happens here. I mean, the process is still exactly the same.
Yeah, 3 pi over 4 and 7 pi over 4, right? And 3 pi over 4 and 7 pi over 4.
Well, at negative 1, this isn't tangent. This is just cosine, right?
Yeah, wait, whoa. Wait. Oh, no, it is of it.
So negative 1, you're just gonna add. That's it.
That is correct. Right?
I forgot that.
It's easy when you have just done that. So, look at it again.
But that's no guarantee.
Oh my god, I'm serious or not? No, I think it is.
It is no solution.
Hey, it is no solution. Yes! Wait, okay. I got it, but I got it on the unit circle. No, she did that. I got it with like 2 pi and the 2 pi is not allowed, so this is
Right.
Oh, there's the unit circle.
I don't think I got it the same way you did.
Well, we still got it. It doesn't matter how we get there. Well, I got it.
It doesn't matter, like, most of the points are involved in how you get that point, not.
No, yeah, actually. Okay, but what if I'm just smarter than that? I don't want fun, but I'm sure. Stop. Yeah, you get up for.
That's what we should. Go.
All right. So here, of course, we subtract 3 and then divide by 3. So we get cosine of x over 2 is equal to negative 1. All right. Where does cosine equal negative 1? At pi. Okay. So we say, all right, well, x over 2 is equal to pi. So here, to solve for x, we multiply both sides by 2, and x is equal to 2 pi, which is not included in our interval. All right, so can't use it. All right, now our period, again, is 2 pi divided by our b, which is 1/2, which is 4 pi. All right, well, if I add 4 pi to this, I get 6 pi, too big. If I subtract 4 pi from this, I get negative 2 pi, it's still not between 0 and 2 pi. So here we would actually say no solution. Now, I do want to, again, reiterate that there's only no solution on 0 to 2 pi. Yes, right? There are infinite solutions, right? 2 pi, 6 pi, 10 pi, 14 pi, negative 2 pi, negative 6 pi, negative 10 pi, right? There are infinite solutions, just none on the interval that they were given, that we were given. Okay, so I don't want you to confuse it that like are no solutions to this equation. There are, all right, just none that where we're looking. Well, for instance, what if this were 2x instead of x over 2? Well, now your period would be pi. So if you subtracted pi, you would get pi. And if you subtracted pi again, you would get 0, right? So 0 and pi would actually be solutions. Now, of course, if it were 2 pi here, you would have multiplied it by, I mean, if you had 2x, your period would be pi, but your here you would have had pi over 2, right? So that would have fallen in that range anyway. So typically that's how it's going to work, but you do kind of want to be careful and make sure that you check yourself. And that's it.
Booyah.
All right.
The 0 to pi, will that always be 0 to pi?
No, sometimes it could be all solutions. So if they say, so for instance, let's actually just do this under that case. Okay, so let's change this. All right, and let's say, of course we could have left that, but let's say that the direction said find all solutions. Now, and I think we're going to deal with this a lot more on Monday, okay, but just for the time being. So here we say, okay, well, we know x is 2 pi, and we already know that our period is 4 pi. All right. Well, all you have to do is say, okay, well, take each solution, like sometimes how you have multiple of them. You just take each solution and you say, okay, well, plus or minus n times your period. So in this case, 4n pi. And then that gives you your infinite solutions. That's all. Like, it's actually easier, I think. Yeah. But we'll talk a lot more about that on Monday.